Hello, my name is Nathan Dunnigan, and this is my Lab 3 on a black hole. The introduction will examine the purposes of the lab and the different equations and fundamental principles used in this lab. It is important to note that the system is defined as the object that the net forces are acting on. In part 1, the star is the system as the black hole is acting as the surroundings, and then in part 2, we are trying to find the net forces acting on both the planet and spaceship, which will allow us to see the trajectory of these two systems, which will then allow us to estimate the initial velocity on the spaceship so that the spaceship does not crash or get sucked into the black hole. The purpose of part 1 is to find the mass of the black hole, and the purpose of part 2 is to determine the initial velocity needed of our spaceship in order to not get sucked into the black hole or crash into the orbiting planet. The first fundamental principle we will be using is the momentum principle. We know that momentum is equal to mass times velocity, and net force is equal to the change in momentum over the change in time. We will also need to know the formulas for perpendicular and parallel forces. We know that net force is equal to the F net parallel plus F net perpendicular. This can be then used to say that dP over dt is equal to dP dt parallel plus dP dt perpendicular. This can be further expanded by the product rule using derivatives as seen here. This emphasizes the equations from above and the meaning of the parallel net force, which shows the speeding up or slowing down, and the perpendicular net force, which shows the direction, and the centripetal force, which is the name given to any force which causes a change in direction of velocity towards the center of the circular motion, and the component of the force which is perpendicular to the velocity is the part resulting in the centripetal force. We will also be using the universal gravitational force formula and principle, which is the force felt by the system due to the mass of another object. We know the component of g as it is the gravitation constant given, and with the formula below we will rearrange it in order to find the actual mass of the black hole, which is the one unknown for part 1. We will also use the velocity and position update formulas in the second part of this lab. We can find the final velocity of a system if we have its initial velocity, net force, mass, and change in time. We will utilize the position update formula with a non-constant net force, which is why the average velocity is equal to the final velocity, where we can find the final position of an object if we have its initial position, final velocity, and delta t. For the brief model description and preview, we will be using the gravitational force formula, net force formula, and Newton's second law to solve for the unknown mass of the black hole, and my previewed mass is below. And for part 2, we will be using the same formulas to compute the required initial velocity of the spaceship in order to get as close as possible to the black hole without getting sucked in, and my previewed correct initial velocity of the spaceship is below. The reasoning behind the assumptions and principles I used are below. We needed to use the universal gravitational formula in order to find the unknown mass. We needed to use Newton's second law momentum principle to find the net forces that would be used in the gravitational formula, as well as finding net forces on the planet and spaceship in part 2, and we needed to use the update formulas to keep the objects moving in part 2 in order to approximate the initial velocity. We first look at the initial conditions of part 1 of the lab. The first thing I did was change the variable c to my email, as we are required to do so in order to generate a unique star trajectory. We know the gravitational constant and mass of the star as these are given to us. I then edited delta t to be equal to 1 day in seconds. For the calculation loop in part 1, we will use the formulas that were talked about earlier. We will find the initial and final momentum by multiplying the star mass by the initial and final velocity. We will calculate the change in momentum and velocity by subtracting the initial values from the final values. We will calculate dP over dt and F net by using the formulas in the introduction. Then to find dP over dt parallel, we multiply p hat by the magnitude of p over time, and this is also equal to F net parallel, and then subtract this from dP dt to find the perpendicular components. And then finally, to compute the mass of the black hole, I used a counter and a final mass additioner in order to find the average mass of the black hole by dividing the final mass by the number of times the loop was run, because the mass changes every time the loop runs. Here's the result from part 1. F net is always pointed towards the black hole, which is the orange arrow, and gets bigger as it gets closer, and then its components add to get F net, the parallel and perpendicular forces. And we can see the average mass of the black hole calculation here. One thing to note is that the closer the star is to the black hole, the greater the mass, which is why it is important to average out the mass. For part 2, the initial conditions include the mass of the black hole, which I found from part 1, and the known constants that are given to us, such as the g constant, the planet and ship masses, and delta t. We are also given the planet initial conditions. The spaceship initial conditions were the values that I had to create through trial and error to ensure that the spaceship gets as close to the black hole without crashing or getting sucked in. My answers will be explained later. For the calculation loop in part 2, we first had to calculate the net force on the planet, which is the sum of all the forces acting on the planet. To do this, I used the universal gravitational formula that I talked about in the introduction. Then we have to calculate the net force acting on the ship. Finally, we had to use Newton's second law of the update position and velocity formulas, which I talked about earlier as well, to make the objects move while the time changed. Here are my results for part 2. The top picture shows the zoomed out version with the spaceship path in the magenta color and the planet's orbit in the cyan color. Then I zoomed in to show just how close my spaceship actually got to the black hole. As I mentioned earlier, after trial and error, the correct initial velocity was negative 3.2 e to the 7 in the x direction and 1 e to the 6 in the y direction. The possible sources of error may be that averaging out the mass in part 1 may not be directly equivalent to the actual mass, and then in part 2, guessing through trial and error may not have gotten me as close to the black hole as I could have gotten. We were asked to discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum in its components. The answer is that the net force and rate of change of momentum are technically equivalent. The main difference in this lab is that we are able to directly calculate dp over dt in its components, and just concluded that Fnet was equivalent because we could not directly compute Fnet. For the what-if question, we were told to find the initial velocity of the spaceship in order to enter into some kind of orbit around the black hole without crashing or getting sucked in. I was able to successfully create an orbit around the black hole through trial and error, which was the same method I used for part 2. The initial velocity is below. Thank you.